Today, we work to measure the force between two magnets as a function of the separation between them, and through it find the mathematical relationship between force and distance. First, we need to understand how magnets work. Here you can see a diagram I constructed of forces relating to two magnetic poles. Here is a better diagram which indicates magnetic flux. These magnetic field lines indicate the strength of the magnet. It can be seen that the greatest area of magnetic attraction or repulsion is at the polar regions, at the end of the magnet. So in calculating force, we did the following. A magnet was placed on a scale and its magnetic dipole aligned end to end with another magnet a set distance apart. It was observed that the mass increased as they approached the terminal end of the other. As measurements were subject to error due to imprecise means of measurement, 3 separate trials were conducted and an average mass taken and converted to SI units to calculate force. Force was then calculated as a product of the mass of the magnet at varying distances and the acceleration of Earth due to gravity, which is 9.8 meters per second squared. The equation for magnetic force functions similarly to Coulomb's law, in that the force is inversely proportional to the distance squared. Coulomb's law states that the law of force between electric charges is similar to that of magnets. Therefore, as you can see in the equation here, the magnitude of the force between the two magnetic poles of strength are denoted Q1 and Q2, where C is the proportionality constant. This is also known as the inverse square law, in which the intensity or force in this case is inversely proportional to the square of the distance from the source of the charge. R here indicates the distance between the two magnets, or the separation distance. What this equation entails is that, for example, if the distance between two magnets is doubled, the magnetic force will be 1/2 squared, or 1/4 the original value of force. And if the distance between the two magnets is instead halved, the magnetic force between them will increase to 4 times the initial force, or 4F. You get the idea. It can be observed here that the exponent reaches -4 the greater the distance from the magnet. Approaching the magnet, the exponent reaches -2, which indicates the magnetic field at this point follows an inverse square law. This is because when the magnets get closer, each dipole on the magnet interacts to a greater extent with the dipole on the other. It can be seen that force becomes more constant with distance, in that it follows a linear force the greater the distance from the magnet. However, as the distance decreases, the log graph rolls over and becomes exponential. The equation for a straight line generated here can be rearranged to give force to the inverse power of a value. This gives us the equation illustrating force as a function of separation distance. If magnets could exist as monopoles, it is expected that they would follow an inverse square law, like that of electric charges. However, as magnets have 2 poles at either end, they would exert a force that obeys an inverse to the 4th power law. It is assumed that in large distances, the charges in the dipoles partially cancel out the charges of the other. Essentially, when one magnet is a large distance from the other, the directional inverse square contributions nearly cancel out, hence an inverse to the 4th law. At closer distances, the force exerted by each magnet is cancelled out by the other opposing pole on that same magnet. Therefore, the forces between magnetic poles is inversely proportional to the square of the distance between magnetic poles. The exponents of force and distance as seen earlier are evidence of this. There were a number of complications in the procedure. Firstly, the center-to-center distance of the magnets weren't taken. The top of one magnet was measured and the base of the alternating one. Therefore, the equation generated for the force of this system cannot apply to the center-to-center mass of 2 alternating magnetic dipoles. Additionally, the scale was only sensitive enough to record mass at 16 centimeters and no further. If a more sensitive system were calibrated, it may have allowed greater distances to be recorded, which may have resulted in a force equation closer to the inverse of the 4th power, like expected for this system. In conclusion, the use of inverse proportionality allowed the use of the equation as reference for how the variation in one variable, like distance, could affect another, like force in the scenario of a magnetic field.